Okay, it's the end of the day and I know you're all tired and waiting to have refreshments and everything else, but please pay attention because I need your help. I actually need you to ask as nasty questions as you can because I'm going to present a longer version of this in a week to some not as friendly crowd of logic and computer science types in Netherlands, actually, of all places.
Oh, they're terrible, yeah.
Yeah, they're horrible people. So, which is pretty self-evident from the title, what I'm thinking about, and I've been working for a while now on that topic, is what are the best ways to organize big scientific communities and big scientific networks. Now, if you think about, and in particular, I'm interested in big physics. Now, and a few other places. Okay, so this is how sort of average lab, physics lab looked like at the beginning of the 20th century. You could, in a way, keep it in the family, one or two researchers. This is Marie Curie and her husband. And really, organizational problems never really came up at the level of the laboratory. You know, you can pretty much work it out as you go. But if you fast forward about 100 years, I mean, of course, there was a network of different labs, so you had to communicate in between the labs, so you had organizational problem at that, or sort of questions at that higher level. But now, where you have, nowadays, where you have literally 100 times more physicists than back in those days, way more than the rate of the increase of population, and vastly more resources, you end up with something like this. This is actually a Large Hadron Collider lab at CERN that houses about 10,000, one way or another, 10,000 people. Discovery papers in this lab are signed by 3,500 collaborators, physicists. The latest one. Actually, the latest one was even more than that. So you come up with obvious questions, how you should really organize communities like this one. Now, you also get the sort of problem of the network of all these labs. You have to organize a network of these huge labs as well. The question is that, you know, often it's sort of very politically charged question, is whether organizing science is best left to scientists. And, you know, the sort of usual response is, yeah, of course, you know, let them do their work, that's how they perform best, you know, for the benefit of the society, and funding agencies and sponsors shouldn't really mess too much with the way that they want to do their work. That's really not a good answer, you know, it's sort of a vacuous answer. The real answer is what happens once you you give them money and you let them organize their science. All kinds of things can happen and do happen. So, you know, you have sort of often institutional inertia that shapes your research. You have funding structure that shapes your research. That can be very bad, actually, in terms of the efficiency of your research. You have politics at all levels, actually, shape the organizational sort of level of your research. I can give you numerous examples. One of the examples is actually CERN in its first 15 years of after the commissioning of the lab that actually performed very poorly compared to the US labs. One of the main reasons was that they really needed national representation of each donor nation, right? So you can't really hire based on merit, for example. A number of it changed. It's very complicated, actually, history, very interesting. So the answer is really organizing science is best left to scientists, provided actually that they approach the organizational questions as meticulously as they are subject of research, right? So as sort of, what can philosophers, for example, and similar types do? in order to answer, for example, this question, whether there is actually an optimal way of organizing scientific teams and projects, and how do you actually do that? Well, you can approach this question in two different ways. One is, I would call it a formal approach, right? Where you can do certain simulations and mathematical modeling, and people have been doing that. So you can use, for example, computer simulation with graphs, and then try to figure out how different structures of networks, centralized, less centralized, decentralized, perform with respect to certain kinds of tasks, right, and draw certain conclusions. Or you can use mathematical models, as they do it in economics, for example, and do similar, like wisdom of the crowds and so on, and do similar stuff. Or you can actually do something that I prefer, which is sort of case-based approach. So you study history, for example, of these big labs, you see what kind of different structures of organization existed, and then you can do a sort of empirical or data-driven analysis of particular cases, draw certain conclusions. Now, of course, there are good and bad sides to both of these approaches, and you have to go back and forth, right? If you do case studies, you're going to end up with certain conclusions, but you want them clear, and often they're not very clear, so you use modeling to improve your understanding, you use simulations. The other way around, also, I mean, when you do simulations, your parameters in the simulations are they're not always connected, usually connected in obvious ways to actual cases, right? So, you know, you have to sort of collaborate. So let me give you an example. So there are two sets of questions. One is sort of quantitative questions. For example, optimal team composition. How many members of research group should exist, right? What's the number of researchers in the lab? And there is actually currently very heated debate among biologists. What's the number roughly, or not so roughly, in a biology lab that should really be optimal for the lab? What's too many, what's too few? If you have too few of them, then you end up with sort of like-minded people, or you don't have the kind of cognitive diversity, epistemic diversity. If you have too many of them, you can have lots of diversity, but they can't communicate properly because the group is too small, and then basically diminish the other, or they can hang out for too long actually, if the group, if an experiment, for example, lasts for too long. This is true of any other organization, by the way, corporations as well, political parties, whatever. There are, of course, context-specific conclusions that we can draw. And then finally, there's optimal composition of exploration. You want to discover a particular particle or a fundamental force. How do you organize labs? How many labs is optimal number, you know, for what you want to do? Can you do with one? Sort of the best job, the most. How many of them you need? How organized they should be? What's the size of these bigger projects in your sort of pursuit of the question that you're interested in? A very closely related question concerns something that has been studied in the last 10 years by a number of people, and that's the diversity of groups. How diverse they should be, really. And let me just quote Scott Page, who did a marvelous job on this. So this is what he says. Diversity matters because it can increase the bottom line by introducing more perspectives, heuristics, interpretations, and predictive models. These diverse cognitive tools can in turn improve an organization's ability to solve problems and make accurate predictions. Sounds interesting, sounds like sort of out of a political correctness manual. It's kind of like a platitude. But actually, there's a lots of work actually to show that this is the case. And the first ones to pick out this and to understand this was actually the business community of all places. They know that they have to diversify and they know how to measure it. So, just to give you an example from the same author, this is his diminishing returns diversity theorem. It sounds a bit complicated, but it's not really. And that's the sort of a, if you want kind of formally, bottom line, the most abstract bottom line, why you need diversity in general. So the point of this theorem is that if you have two sets of entities with the same number, you will be, in general, better off in terms of adding the value to the performance of your entities. If another entity you add to the group is of a different type than the already existing entities. In other words, if you add another entity of a type that already exists in the group, your returns, or rather your performance of the group or the contribution to the group will diminish. If you add another one, well, you don't add much value, and then basically you end up with a zero value. Now, of course, this is provided these two assumptions that there are no interactions, right, among the entities. If entities interact, they can interact destructively, constructively, but in general, as a kind of a baseline, this is the motivation why diversity really matters and why one should study how it works in different contexts. It has very real implications. So, two of my graduate students, another, well, he's not a student anymore, computer science person and myself did a sort of a quantitative study, right? That's the sort of a case-based approach I showed there, and data-driven analysis. We worked on the data from one lab, one of the most successful big labs in the history of physics, really, Fermilab in the States. So what we did to see how the composition of the teams actually works out in terms of the efficiency in the lab, we used a particular kind of analysis which is fairly common in the corporate world. So, for example, when they want to assess how a bank branches compare to each other in terms of the efficiency, they have the same inputs, they have the same outputs. Which one is the most efficient? Not only that, but how the others should improve exactly in terms of these inputs to match the efficiency of the other one. That's the method actually that we used. I'm not going to bother you with the details of the method. So our inputs were the number of researchers within an experiment or a project, let's say, the number of teams within a project, and the duration of the project expressed in hours. And we tested or sort of analyzed 27 experiments performed in about span of 15 years. And we selected experiments. We didn't use, for example, calibration experiments because, of course, everybody will cite you, right? I mean, and the output was the weighted citations. Now, of course, you can object, well, citations, they're the measure of, you know, the success and efficiency. That's a legitimate concern. However, we picked physics precisely because physicists fairly quickly, compared to other sciences, converge on what most of them think and keep thinking is the valuable result. For a number of reasons, that's the case. So the weighted citations are divided into 7 groups, whether you're cited in a reputable journal, top journal, and these are the actually categories that physicists themselves produced and they use it. Their archives are impeccable, actually. You can just sort of upload all the data and do the analysis. So to our surprise, the results showed with very significant sort of measure that the most efficient experiments, there were 6 of them, were very small compared to the others. The inefficient ones were all large. When I say small, large, 10 times smaller or 10 times larger, right? That was surprising. Time didn't play much of a role, actually. So, I mean, this is a preliminary study, right? And there are other arguments in favor of this sort of supporting the same kind of a conclusion. So basically you end up with this conclusion. If you want to do particle physics, you're better off to have lots of small experiments and smaller teams, which actually diversify already at the level of choosing their projects, right? Epistemically, that's very advantageous. It seems that a number of smaller groups will get a better idea what hypothesis is worth checking rather than centralized big group, actually, which is sort of very sort of a hierarchical. Or
you're talking about the small numbers of
smaller experiments. So smaller groups designing the experiments.
Smaller groups.
Yes.
Small number of smaller groups.
Not smaller number. You can have but there has to be a fairly small number of the groups actually, which are also sorry. You can have as many as you want as long as they are small. So that's one sort of a preliminary conclusion. And the other one is that you should really have diversity at some level. And it's better, it seems, in this case, to have the diversity already at the level of picking the hypothesis that you want to test, actually, rather than having a big, cumbersome team which is diverse. Because there are all kinds of problems with communication, with how they're going to divide their. Now, you might say, okay, that's all fine, you know, sort of nice, interesting epistemological points, but who cares, because we can't do it that way. The sort of logic of discovery in particle physics pushes us to have these humongous labs, right? You know, you have sort of big goals, you want to discover particular particles that requires high energies, and you need big experiments to do that, right? That's the usual theme. Or to quote a philosopher, in science as in war, big becomes unavoidable, as Nicholas Rescher put it actually in his book. Now, is that really so? First of all, that's not really the case. So physically, in terms of the physics of the case, I'm not going to talk about that now. Things are not really black and white at all. You can actually test standard model property, standard model, which is the sort of dominant theory that you want tested, and that is tested in Large Hadron Collider. You can actually test it in a number of other ways and in smaller labs, and you don't even need high energy for that. You don't even need actually to produce high energy. And that's done, right? But at the sort of a fringe of this big crucial, supposedly, experiment. So this is the argument. Usually high energy is required to study subatomic particles. You need big labs. You end up with a few labs and long-running experiments, counter to everything that epistemology sort of tells us we should really do. Now, the question is then, well, you know, how can you improve this situation? You can improve it you have to improve it much earlier when you create the research teams actually and research labs. There are two ways of doing it. The first one is this, you pour all the resources, build a big lab, and then it evolves over 30 years and it discovers one particle in 30 years or something. Or you can have at the beginning, or you can have a network of independent labs. How do you achieve actually the results, the same results? Actually, physically you can do it in various ways. As far as theory in physics really tells you. As far as technology goes, the innovation is really the key word here. You don't know the limits of technology before you try things. In other words, what you can do instead, you can approach it as sort of a portfolio, as the business sort of people would say. You distribute all the funds that you poured into one lab, big lab, you actually distribute it evenly across the labs and also across the energies at which you experiment. And then you wait long enough, and then from one of these labs at lower energies, you're going to get innovations which are going to reduce the cost of the production of particles at high energies that you need. Now you might say, well, you know, that's interesting. However, is that possible? Not only it's possible, but it happened too late because all the money was spent on the big lab, right? So one way to do it is to build a very different kind of collider than this one, the so-called linear colliders, where you, just to put it very briefly, that gives you a very sharp picture of the interactions you want. The other one gives you a very fuzzy picture. At the time they started planning, they poured all the money into the existing technology. In the meantime, this technology that gives you a sharper, better picture evolved to the extent where it would be at least 50% cheaper to actually do it. But now it's too late because all the money is actually spent. So it's really the matter of strategy and organization rather than some physical limits, you know, or insurmountable technological sort of limits. And that's why it's really important to think very hard about this and not let really the sort of social and political inertia create the sort of a context of your research. And that's really what happens to a great extent in the particle physics, because this big lab that you see is really, in many ways, a replica of the Manhattan Project. That's where physicists learned to build big labs and learned how to attract the funding from the government for these big labs. So to a great extent, they keep doing it the same way they did it when they built the atomic bomb. I mean, historically, that's more than clear, actually, when you read it. So these are all the political reasons. And one sort of a remedy for that would be actually to study the optimal ways with all these tools that we have of epistemology, social epistemology, simulation, and so on. And in conclusion, sort of a takeaway moral of the story is, if you're organizing your research, you should really increase the rate of diversification as much as you can. Can be too much, but we are never really even near to that. And if you should really think about in advance, and as meticulously as you do your research on the subject, how things should be composed and how you should really diversify. Well, you know, just simulate, analyze, you know, experiment and do whatever scientists are normally doing. So that's it.